Gauss's law, integral around a closed surface of E dot dA equals Q enclosed over epsilon naught. Now you know it. We've played with it. We've thought about fluxes on this side. We've thought about the charged enclosed. We've written fun homework problems relating the two. And that's really good stuff. I mean, I could do that for a couple days and not get bored. That's good. But it's really not what Gauss's law, it's really not the big powerful thing Gauss's law can do. What Gauss's law is really good for is calculating the electric field. And that's not obvious from looking at the equation, because the E field is buried in this surface integral, this big vector calculus mess. You can't solve this for the E field in terms of writing E equals. Right? But it turns out it is actually very powerful for finding the E field, but to do it, you have to really understand how the vector calculus works. Okay? So let me show you how that works. We are going to do Gauss's law for a point charge. So we're going to use Gauss's law to find the E field. All right? So the charge, it's not really a point. It's just a small charge that I've been drawing the whole time, a little plus Q. Okay? So the first step in using Gauss's law to find an E field is to draw a Gaussian surface. All that means is the closed surface over which you're going to apply Gauss's law. In addition to naming the law after Gauss, they name the surface after Gauss. That's all it is. It's nothing special. It has to be closed, is the one special thing. And choosing the Gaussian surface is the most important part of this. If you choose the right one, it'll be fine. If you choose the wrong one, it won't work. So knowing how to choose the right one is a little bit of wisdom. Okay? We can't write a formula for everything you need to know how to do in physics. There is a little bit of experience and wisdom involved. And the wise person would tell you to use symmetry. Okay? So first I'm just going to give you the surface. I'm going to talk about why we chose it. And then you'll get some experience and you'll see how to find the right symmetry. So in this case, it's a sphere centered on Q with radius R. Okay? So let me draw such a sphere around Q like this, like that. And it's a three-dimensional sphere. It's a three-dimensional surface going around Q. Okay? And it has a radius R. That's our Gaussian surface. So now we have to come over here and apply Gauss's law. So the right side is not too hard. That's the plus Q is the charge enclosed over epsilon naught. But we also have to do the left side. Okay? We have to think about the surface integral. So what we rely on is symmetry. This surface was chosen because it has a symmetry that matches a point charge. So symmetry of our Gaussian surface is going to tell us two things. First, we're going to use it to deal with this dot product. This dot product means we have the E field vector and the dA vector. We take the dot product of those two vectors. So it turns out everywhere you go on a sphere, dA sticks out, right? So if we were to tile this up like the disco ball into little squares, every little square we would draw the dA sticking normal to the surface. So dA is like that, dA is like that, dA is like that. It sticks out. But also due to symmetry, the electric field would always stick out. Okay? And that's a little bit trickier to see just based on symmetry. Basically what I'm doing is I'm using Gauss's law to derive Coulomb's law. And you may say I'm cheating. You may say, well, you're assuming Coulomb's law by saying which way the E field points, but I'm really not. I'm really using symmetry because forget all the surfaces there, forget the whole universe is here. Well, don't forget the universe here. Forget the whole lecture hall's here. We have a charge at one position and we have a point at another position. They're on an axis, the line between them. And you ask yourself, which way is the E field going to point there? And the answer is due to symmetry, it could only point this way, away if it's a positive charge, or it could possibly point that way if it's a negative charge. But it can't point any other way because there's no reason for it to point any other way. It can't have a component this way because there's nothing special about this way. The charge is here. If you gave it a component this way, there's no reason you couldn't give it one that way. Right? The symmetry tells you you can't have sideways components because the charge looks the same no matter where you go around that axis. So really, it has to be due to symmetry that the E field always sticks out. And that's true anywhere you go. Due to symmetry right here, the E field has to stick out. And due to symmetry right here, the E field has to stick out. So due to symmetry of a sphere and the charge being at the center, E is always parallel to dA. Okay? And that rule lets us simplify the integral a little bit. It lets us say it's the integral around a closed surface, and now that we know that E is parallel to dA, that means the angle between them is 0 and the cosine of 0 is 1. Really, we're talking about their magnitudes of E, the magnitude of dA, and then the cosine of 0 is 1. So you just leave it there, or you don't write it. There's a 1 there. So what we've done is use symmetry and the fact that these two are parallel to take out the dot product. Okay? But we're not done. We still can't do this integral because we have to integrate over the area, and what is E doing? E could be a function of area. So we have to go a little bit further. What else can symmetry tell us about this E field on the surface? It can tell us about the magnitude. Symmetry also tells us that E magnitude is constant on the surface. And why? Because anywhere you go on the surface, if you're right here, you're a distance r from the charge. So you're going to have some E field. If you're right here, you're a distance r from the charge. If you're right here, you're a distance r from the charge. Anywhere you go physically is no different from any other place you go. So there's no reason that the E field would change. There's nothing special about this place relative to this place. They're all the same place. So the E field has to be the same everywhere you go. If the E field's the same everywhere you go, you can take it out of the integral. Okay? So now we have the E field magnitude times the integral around the surface of dA magnitude equals Q over epsilon naught. Aha! Now that it's out of the integral, we can solve for it. Right? We can now solve for the magnitude of E. And actually this integral now became not so hard. It's just the integral of dA over a surface. You don't even have to write it in any fancy coordinates. It's just the area of a surface. Okay? So now we could write it like this. We could say the magnitude of E equals times the area of a surface of a sphere, 4 pi r squared is the area of a sphere, equals Q over epsilon naught. All right. And now the big ending, I've left myself no room. I'm going to write it on here. It's so exciting. I'm going to put it right here. Is that the magnitude of E equals 1 over 4 pi epsilon naught times Q over r squared. And that's Coulomb's law. If you're obsessed with Coulomb's constant, remember this is Coulomb's constant. Ke is just the convenient way to write 1 over 4 pi epsilon naught. And it's easier to remember because it's 9 times 10 to the 9. But this is how you'll see it in a lot of books. 1 over 4 pi epsilon naught, Q over r squared. It's just the magnitude of the electric field. The direction we actually know from symmetry. So it doesn't fully look like Coulomb's law because we aren't doing it as a vector. But I could just say by symmetry, I could make it a vector that way, by symmetry. So that's an example of how we used Coulomb's law. Even though the electric field is stuck in this vector calculus formula, we used symmetry to get the magnitude of the electric field out. And it actually gave us the electric field everywhere because we did it for one radius, but it would be true for all radii. There's no special radius where this is true. It's symmetric for any radius. So we actually got a general solution that's true, in this case, in all space, in all radii spherically symmetric around the point charge. So you see Gauss's law is actually very powerful. You can calculate many E fields in many situations, and we're going to cover a few of them.